Hi everyone. So today we're going to focus on covalent bonding, more specifically how the atoms are bonded within a molecule. So what we're going to learn how to do today is how to construct a Lewis structure. A Lewis structure is essentially going to be a diagram kind of showing how atoms are bonded within a molecule. We have to keep in mind what's called the Octet Rule. So the Octet Rule is essentially stating that all the atoms want to have 8 valence electrons or have that full shell on them. So when we are diagramming our molecules, we want to make sure that all the atoms essentially have their valence shell filled. And a Lewis structure is able to show the types of bonds that the atoms are sharing, in which the electrons are being shared, but also unshared pairs of electrons. So drawing Lewis structures comes down to just a few steps. I put these steps together based on what I usually follow, trying to be as general as possible in the order. So the first step, because of the fact that the valence electrons are the ones that go into bonding, we need to know how many valence electrons we're going to have. So we have to determine the total number of valence electrons within the molecule. Secondly, we have to be able to identify the central atom. So the entire molecule will have this central atom as like its anchor. So we want to know which atom is going to be at the midpoint of it all. Once we've identified the central atom, we want to connect all the atoms to it, unless there is a group present in which there are other atoms bonded to portions of that group in which the group has its own central atom. Once all the atoms are at least connected together by a single bond, we're going to distribute the remaining pairs of electrons to the atoms that still do not have a full octet or a full shell after bonding. And then lastly, after distributing out all the electrons, we want to check to see if all the atoms have a full valence shell, and if they don't, we may have to use multiple bonds. So let's take a look at an example here for CH4. So first off, going into step 1, we want to identify the total number of valence electrons. Well, carbon has got 4 valence electrons, and hydrogen has 1 valence electron. But there are 4 hydrogens in CH4, so the hydrogens together are bringing 4 valence electrons. So in total for CH4, we have 8 valence electrons to use. So identifying the central atom comes down to the formula. The first atom listed is usually going to be your center, but there is an exception. So hydrogen cannot be a center. Hydrogen is way too small and can only hold 2 valence electrons. So when hydrogen is listed first, it can't be the central atom. We just kind of move on to the next element here. So carbon is the center, and then the remaining atoms get distributed around your center. So these 4 hydrogens are going to be distributed around the carbon. Next, we want to make sure that everything is connected to the middle. So we're going to use lines here to connect it. These lines represent what's called a single bond. And so this line, the single bond, is tethering the atoms together. Within a single bond, 2 electrons are being shared among the atoms. So that means any atom that's connected to a single bond has claim to both electrons in it. So just using up all the bonds, we have used up 2, 4, 6, and 8 electrons. So we began with 8 valence electrons. Bonding has used up 8 valence electrons, so there are 0 electrons remaining to distribute. Now, since hydrogen only has the one-s orbital that can hold 2 electrons, having a single bond is all that hydrogen can do. So for hydrogen, a single bond means it has a full shell. So all of these hydrogens currently have their shells full. Then it's time to check on the carbon. The carbon has 4 single bonds to it, which means the carbon has 8 valence electrons on it currently, which means carbon shell is full. So now, the fact that we have distributed all the electrons and every atom has a full shell means our Lewis structure is complete. This is the structure for CH4. So let's go to another example, Cl2. So chlorine has got 7 valence electrons, but there are 2 of those, so we're going to have 14 valence electrons. So typically our structure is going to have an even number of valence electrons. Everything's going to be distributed out as a pair. So it's a good way to check that we're even starting off the right way that our total number of valence electrons should be an even number. So Cl2 has got 2 atoms to it. So chlorine, chlorine, we're going to connect them with a single bond. So of our 14 electrons, we have just used up 2 electrons just bonding, which means we have 12 electrons left to distribute. Now if we examine this left side chlorine only has 2 electrons from the bond, meaning for a full shell it's going to need 6 more. So let's go ahead and we're going to give it pairs of electrons. And we're going to give it 3 pairs or 6 electrons. These pairs are called lone pairs. They're basically pairs of electrons that belong to that lone atom. These are 2 electrons that are being unshared. So the electrons in the bond belong to both atoms, whereas the electrons in these lone pairs only belong to that one atom. Okay, so of our 12 electrons, we have just given 6 to the left chlorine, meaning we have 6 remaining. And now if we take a look at the right chlorine, it also only has 2 electrons, so it's going to need 6 more in order to get all the way up to 8. Okay, so of our 6 electrons, we have just given up 6. We have 0 electrons remaining. If we check the left-hand side, this chlorine's got 2, 4, 6, 8 electrons. And if we check the right-hand side, this chlorine's got 2, 4, 6, 8 electrons. So 0 electrons remaining. Both atoms are satisfied. Here's our little structure for Cl2. So now let's move on to NH3. So N has got 5 valence electrons. H has got 1 valence electron, but there are 3 of those, meaning all the hydrogens bring together 3. So in total, we're going to have 8 valence electrons again. Okay. So as for a central atom, nitrogen is first, nitrogen is our center, and we're going to have these 3 H's distributed around the nitrogen. Okay, so we're going to single bond connect everything to the nitrogen. Of our 8 electrons, we have used up 6 just bonding, meaning we have 2 electrons remaining. So we have to give out these 2 electrons to an atom that does not have a full shell yet. So once again, the hydrogens only need 2 electrons because all they have is a 1s orbital. And so this hydrogen is filled, so is this one and this down one over here. Nitrogen, though, has 2, 4, 6 electrons. It needs to get up to 8, which means it needs 2 more electrons. Luckily, we have 2 electrons left. So we can just go ahead and donate those last 2 to the nitrogen. Okay, so now we've got 0 electrons left to distribute. Everything now has a full shell. Here's our NH3 structure. So here's another example covering O2. So we're going to go ahead and get the number of valence electrons. Oxygen's got 6 valence electrons times 2 oxygen means we're going to have 12 valence electrons. Okay, so oxygen, oxygen, single bond connected. Of our 12, we have used up 2 bonding, meaning we have 10 electrons remaining. Okay, so left hand oxygen has only 2 valence electrons from this bond, so it's going to need 6 more to get up to the 8 valence. Hand out 6 of our 10. We have used up 6, meaning there's 4 left. Right. On the right hand side, okay, this oxygen has only 2. It needs 6 more to get up to 8. However, we've only got 4. So I'm just going to give it whatever we have left. So now we've got 0 electrons remaining. So if we take a look at the left the left oxygen, it's got 2, 4, 6, 8. This oxygen is satisfied, but the right-hand carbon's only got 2, 4, and 6. So it is not filled yet. We cannot just add an extra pair of electrons because we have 0 electrons left. But this right carbon isn't filled. This right oxygen isn't filled. So then how do we solve this problem? Well, if an atom is still lacking after all of the electrons have been distributed, more sharing is needed. Sharing takes the form of a bond. So essentially, a lone pair of electrons goes from being an unshared pair into a shared pair, or an additional bond. This is called a double bond. A double bond is essentially an extra bond of sharing. So there are 4 electrons being shared now as opposed to just 2 with a single bond. So now the left oxygen still has 2, 4, 6, and 8, but now this right oxygen needs 2, 4, 6, and 8, so it's also filled. So adding multiple bonds increases the sharing of electrons, and sometimes it's necessary. Okay, and then our last example here, N2. So N has got 5 valence electrons, 2 N's here, which means we have a total of 10 electrons. Okay, so N, single bond them. Okay, so we have used up 2 in just bonding, 8 electrons left. Okay, left-hand nitrogen needs 6 more, it's only got 2. So of our 8, we've used up 6, we've got 2 remaining. This right oxygen also needs up to 6, however we've only got 2, so we're just going to go ahead and give it what we have. Okay, so a quick check. Left hand side has 2, 4, 6, 8. Right hand side only has 2 and 4. We cannot add any more lone pairs here because we have 0 electrons remaining. So once again, we're going to have to increase our sharing. Okay, so a lone pair, we're going to turn it from an unshared pair to a shared pair. Okay, so let's check to make sure that worked. Left nitrogen, 2, 4, 6, 8. Right nitrogen, 2, 4, 6. So one additional bond of sharing was not enough. So that means just share some more. So another lone pair is going to essentially become another bond. So now we've got 2, 4, 6, 8 for the left-hand side, 2, 4, 6, 8 for the right-hand side. So here we needed a third bond called a triple bond. So the triple bond is just going to be 6 electrons being shared. So the triple bond is the highest bond. Okay, there is no quadruple bond, but it gives you a maximum of 6 electrons being shared. So sometimes additional bonding is needed, but it is really the last step after all the electrons have been distributed. If the multiple bonds are done before electrons have been distributed, you may not use up all of your valence electrons. So when doing these, you always want to make the multiple bonds the last step. You want to ensure that all the electrons are handed out as pairs first, and then check to see if atoms are still lacking in their octet. If they are, then it's okay to use multiple bonds.